All right, now we're on to E1 reactions. What is an E1 reaction? How does the mechanism work? Well, you've already seen SN1, you've already seen SN2, E2. So I actually think that you guys can probably fill out everything on this page without me. So give it a go with the stuff that's right here. Pause it, do that, and then restart. All right. Unimolecular, what does that mean? That means that there is one reactant in the rate determining step. And based on our knowledge of SN1, this is probably going to work in a really similar way. So how would that maybe work? Well, how does SN1 work? What's the first step? The first step is the iodide leaves. The leaving group leaves. That's step one. And what is the rate determining step in an SN1 reaction? It's this first step because breaking bonds takes energy. So once that leaves, this is the rate determining step. We can call it step one. That's going to produce this carbocation, I minus, and there's also some H2O around. So how do we get up to here? Well, we have to pull off a proton because there's only a CH2 here, but all three of those have CH3. So beta to that iodide are a bunch of hydrogens. So a water molecule can grab that hydrogen and do the elimination to provide that product. So this is step two. So what is the rate equal to then? Well, rate is equal to the rate constant K multiplied by the reactants in the rate determining step. What is that? That's just this alkyl iodide. So that would be the rate equation for an SN1 reaction. Now let's look at what the reaction coordinate diagram would look like. I'll be back with that in 1 minute. All right, so you have the mechanism, you have the rate, you have what unimolecular means. If we had a reaction coordinate diagram, how many hills would be in that reaction coordinate diagram? On the course packet, I have A0, B1, C2, D3. How many hills? Pause it. You did that. Come back. All right. Yep, you are correct. There should be 2 hills. So now I'm going to draw 3 reaction coordinate diagrams, and we are going to select the one that is correct. And in this case, I'm going to say this is an exothermic reaction. Exothermic reaction. So you'll see 3 options in 1 minute. All right, I put up 3 reaction coordinate diagrams. We'll call them A, B, and C. Which one is most likely our the reaction coordinate diagram you would expect for an E1 reaction like the one we talked about up there? So you paused, you decided, now you're back. So let's get rid of the ones that don't make sense. C, why does that not make sense? Yeah, what's the rate determining step? Yep, the first step, and the activation energy for the first step in this third one is actually lower than the activation energy for the second step. So EA is lower here, and we know that the first step is the rate determining step. So that's out. What about this one versus that one? Yeah, they're pretty similar, right? They both have 2 steps. They both have the first one is the rate determining step. So how do we know which one's correct? So what's the major difference? The major difference is the energy of the intermediates, right? Here we have the first step's rate determining, and we have our intermediates here. This one, first step's rate determining, we have our intermediates here. Well, are our intermediates high energy species or low energy species? Well, carbocation doesn't have an octet. It's lost a bond. It took energy to do that. So those intermediates must be high in energy. We have a charged intermediate. Carbon wants a full octet. We have our... So essentially the high energy nature of our intermediates means that this one would likely be the reaction coordinate, whereas this one our intermediates are not of a lower energy than our starting material. So that's why we would be able to get rid of that one. So this would be the most likely reaction coordinate. You should trace that into your course note packet. Yeah, and then we'll keep talking about E1 reactions. We're going to move on to the rate stuff.